The cold of mountain tops and mountain passes and the warmth of the lower elevations. Combined with water, they provide us beauty and recreational opportunities, with snow in the winter and rain in the spring, freezing, thawing. But what does all this weather do to our roads? The problem is essentially one of water in the pavement structure. This Federal Highway Administration sketch shows that water in pavements can come from numerous sources, such as surface infiltration from rain or melting snow, lateral seepage, and capillary actions in soils carrying water up toward the pavement structure from below. Certainly, water-related pavement distress is not limited to winter freeze and spring thaw. However, these time periods can bring unique pavement problems, such as frost heaves, and pavement weakening due to excessive amounts of moisture in the pavement during the thawing period. This video will discuss these cold weather-related pavement problems and will present guidelines developed from recent research that are intended to help road maintenance personnel from state departments of transportation, cities, and counties deal with similar problems. Frost heaving in pavements may be relatively uniform and may appear in the form of longitudinal cracks near the pavement edge, or as heaves and cracks following the flow of groundwater, which result in traffic signs like this. During the spring thaw, large quantities of snow and ice become ample sources of water. In this street in Anchorage, Alaska, the meltwater has little opportunity to drain away from the pavement. The result of so much water in poor subsurface and surface drainage can be badly deteriorated pavement, such as these flexible pavements in Ontario, these in Wisconsin, and these in Maine. Two options are available to reduce or eliminate pavement deterioration during the thaw period. Highway departments can either design and build pavements to resist these effects or restrict truckloads. Since many agencies cannot afford the first option, truck weight reductions are often used during the late winter through part of the spring. These truck weight restrictions are generally posted on the affected route, such as this state route in central Washington, this city street in Anchorage, and this state route in Minnesota. Some agencies, such as the U.S. Forest Service, must completely close selected routes to loaded trucks. In general, maintenance personnel have a good idea of where to apply restrictions, but they often don't know how much to restrict loads, when the load restrictions are needed, or how long to enforce them. The study we will discuss found some possible answers to these questions. First, however, we need to understand the problem. Frost heaving results from accumulation of ice in pavement layers during freezing weather and generally requires three conditions to occur. 1, freezing temperatures, 2, water, and 3, a frost-susceptible soil. Most frost-susceptible soils are silt, such as in the soil in this roadside slope in northern Washington. Frost heave is difficult to totally eliminate. Therefore, agencies generally try to reduce its size and make it more uniform. Differential heave is likely to occur at locations such as abrupt transitions from cuts to fills with groundwater close to the surface, where subgrades change from clean sand or gravels to silts, or where excavation exposes water-bearing strata and bridge approaches. Frost heaves measured at the pavement surface can easily range up to 6 inches or more, like the heaves on this state highway. A second spring-related pavement problem is weakening of the pavement structure. This can be caused by excessive moisture from thawing ice or water infiltration from the surface when temperatures reach a thawing point. Thawing can proceed from the top down or from the bottom up, depending on the pavement surface temperature. During a sudden spring thaw, melting will occur mostly from the surface downward. This leads to poor drainage conditions. The frozen soil beneath the thawed layer can trap water released by the melting ice lenses so that lateral and surface drainage are the only paths the water can take. Thawing can produce a rapid decrease in pavement strength below summer-fall conditions, followed by a gradual recovery over a period of weeks. Here is one result of thaw-weakened pavement. This bituminous surface treatment is potholed and very rough during the thawing period. The Washington State Transportation Center researched these cold weather problems with the intent of designing methods to help you deal with them. Since one option for combating these problems is to restrict heavy loads during thaw periods, the study's objectives were to provide guidelines to city and county governments on establishing pavement weight restriction policies. The underlying assumption of the study was that local governments cannot afford to reconstruct water-damaged pavement structures and must opt to restrict truck weights to preserve their pavement investment. A secondary assumption was that local governments have limited testing equipment and personnel to use in applying seasonal load restrictions. The study surveyed other states and local governments to find the most common seasonal load restriction practices. First, where are load restrictions normally used in the United States? A 1985 survey showed that the shaded states use load restrictions. Interestingly, this coincides with the area north of the 40-degree latitude line. The survey asked about the types of pavement failures the states experienced, their highway characteristics, design information, and their load restriction criteria. The principal kinds of pavement failures reported by the agencies included alligator cracking, rutting, frost boils, and potholes. The states were asked what types of roads they used load restrictions on. The study found that load restrictions are applied to both primary and secondary roads, but mostly secondary. State agencies generally apply load restrictions to roads with an average daily traffic less than 2,500, with 10% trucks or less. Local city and county agencies apply restrictions to roads with an average daily traffic up to 30,000, with up to 10% trucks. Primarily, load restrictions are applied to pavements which have subgrades of moisture-sensitive silt or clay. Load restrictions are normally applied to aggregate and asphalt surfaced roads. Most Portland cement concrete pavements have a structure strong enough to withstand the critical thaw period. This Portland cement concrete pavement near Spokane, Washington is a good example. It is in an area where many flexible pavements experience some seasonal pavement distress. However, this pavement has provided over 50 years of service without the need for load restrictions. Load restrictions are generally applied to pavement cross-sections ranging from 2 to 4 inches of surfacing and 6 to 12 inches of base. Thicker pavements apparently have sufficient strength to overcome the thaw weakening period. Some of the state agencies design pavements for partial frost protection, but most local agencies do not consider frost protection in their design procedures. The pavements that receive load restrictions tend to be 10 to 20 years old or older. In some cases, they are farm-to-market roads constructed just after World War II. For most agencies, normal load limits are 18,000 to 20,000 pounds on a single axle and 34,000 pounds on tandem axles. Spring load restrictions generally range from 10,000 to 14,000 pounds for single axles and 18,000 to 28,000 pounds for tandem axles. Weight is reduced 30 to 50% for single axles and 18 to 47% for tandem axles. The basis for starting a load restriction varies from judging the presence of water coming through cracks and joints to the use of deflection measurements. The majority of the agencies rely on the judgment and experience of field personnel. Maintenance personnel look for signs such as these to initiate load restrictions. Here, water is draining from cracks in the pavement surface during the spring thaw. This pavement has water present at the beginning of the thaw period in alligator-cracked areas. Load restrictions are removed based on the judgment of field personnel, deflection measurements, or when sufficient political pressure mounts. Deflection measurements are made with equipment such as the Binkelman beam, the Dynaflect, and the falling weight deflectometer. Using information taken from other reports, the survey of other states, cities, counties, and provinces, and analysis, the study formulated load restriction guidelines. These guidelines include where to apply load restrictions, how much load restriction to use, and when to apply and remove load restrictions. The guidelines are general in scope and are not intended to be absolute, since the nature of the problem is site-specific. The criteria that you should consider when selecting where to use load restrictions include the depth of freeze, which we will discuss shortly, the surface and base thickness, whether the pavements are on fine-grained subgrades such as silts and clays, local experience relating to observed moisture and pavement distress, and deflection measurements. The load reductions used by the agencies surveyed ranged from about 20 to 60%. The average load reduction for 7 multi-state areas was approximately 44%. The analysis performed in the study supported these figures. This suggests that reducing the load on individual axles by about 40 to 50% reduces the associated pavement stress to levels that preclude or reduce the pavement damage. If load restrictions are to be used, a minimum load reduction of 20% seems to be necessary. On the other hand, load reductions greater than 60% appear to be excessive. To understand when to apply and remove load restrictions, you need to understand a couple of concepts to characterize freezing and thawing. The first of these concepts is freezing index. Freezing index is based on air temperature, is measured in units by degree Fahrenheit days, and is used to characterize how severe a winter's weather has been. Freezing index can also be used to estimate the depth of ground freezing beneath the pavement structure at any time during freezing weather. Such estimates are important in the guidelines to be presented shortly. Freezing index is the addition of the differences between 32 degrees Fahrenheit and the average daily temperature for every day of the entire winter. The average air temperature is the average of the low and high daily temperatures. For our example, on the first day, a low temperature of 14 degrees and a high of 30 degrees results in an average temperature for the day of 22 degrees Fahrenheit. For the second day, a low temperature of 4 degrees and a high temperature of 20 degrees gives us an average of 12 degrees Fahrenheit. In our example, the time period is 2 days. The average air temperatures for these days are 22 and 12 degrees, and the reference for calculating freezing index is 32 degrees Fahrenheit. The reference temperature minus the average temperature for the first day, 32 minus 22, equals 10 degrees Fahrenheit. The reference temperature minus the average temperature for the second day, 32 minus 12 degrees, equals 20 degrees. The freezing index equals the addition of these numbers. 10 degree Fahrenheit days plus 20 degree Fahrenheit days equals the freezing index, 30 degree Fahrenheit days. The complete freezing index for the winter equals the addition of these daily values over the entire winter. The significance of the freezing index is shown here for a thin, flexible pavement, as shown on the right. The plot on the left, of freezing depth versus the freezing index, shows that a freezing index of 400 degrees Fahrenheit days results in an estimated freezing depth of about 20 inches. This sketch of the U.S. shows the area where the average freezing index can be expected to equal or exceed 400 degree Fahrenheit days. Within the shaded area, freezing depths can be expected to exceed the total thickness of the pavement by a substantial amount, which may increase the need for road restrictions. The second climate-related concept is thawing index, which is used to characterize the heating effects of spring's warmer temperatures and can be used to estimate the depth of ground thawing. It is also measured in units of degree Fahrenheit days. The thawing index is extensively used in the guidelines. Thawing index is the addition of the difference between the average daily temperature and a reference temperature of 29 degrees Fahrenheit for each day of the thawing period. As you can see, thawing index is calculated similarly to freezing index. However, it is used for the thawing period. The reference temperature is subtracted from the average daily temperature, and the reference temperature is 29 degrees rather than 32 degrees Fahrenheit used for the freezing index. 29 degrees is used instead of 32 for the thawing index because 29 degrees accounts for pavement surface heating. In other words, when the air temperature is 29 degrees, the pavement surface is about 32 degrees and pavement thawing begins. Similar to the freezing index, the average air temperature is calculated as the average of the low and high daily temperatures. Our example for day 1 is a low of 30 and a high of 40 degrees. This results in an average daily temperature of 35 degrees Fahrenheit. For the second day of the thawing period example, the average temperature is 40 degrees Fahrenheit. In our example, the time period is 2 days. The average air temperatures for those 2 days are 35 and 40 degrees, and the reference temperature is 29 degrees Fahrenheit. To calculate the thawing index, we subtract the reference temperature from day 1's average temperature. 35 minus 29 equals 6 degrees Fahrenheit. The corresponding number for day 2 is 11 degrees Fahrenheit. Adding these numbers, 6 plus 11, gives us a thawing index of 17 degree Fahrenheit days. A more complete thawing index equals the addition of these daily values over the entire thawing period. The study developed guidelines on when to apply and remove load restrictions. The guidelines on when to apply load restrictions are based on air temperature data that are easily obtainable from local weather stations or site-specific high-low recording thermometers. The study derived 2 possible times to apply load restrictions, the time when you should apply load restrictions and the time when you must apply them. Both are based on the thawing index and whether the pavement is thin or thick. The definition of a thin pavement is that it has a surfacing depth of 2 inches or less and a base course thickness of 6 inches or less. A thick pavement has a surfacing depth greater than 2 inches and a base course thickness greater than 6 inches. You should apply load restrictions after thin pavements accumulate a thawing index of 10 degree Fahrenheit days and thick pavements accumulate a thawing index of 25 degree Fahrenheit days following the start of the thawing period. This is used to estimate the amount of thaw to the bottom of the base course. You must apply load restrictions if you want to prevent damage after thin pavements accumulate a thawing index of 40 degree Fahrenheit days and thick pavements accumulate 50 degree Fahrenheit days following the start of the thawing period. This is used to estimate the amount of thaw to approximately 4 inches below the bottom of the base course. These criteria are best suited for use during the normal start of the spring thaw period, generally late February to April, and they are best applied to fine-grained subgrades such as silts and clays. When to remove load restrictions is site-specific and difficult to estimate. Probably the most accurate method for you to use in making this determination is measuring pavement surface deflections. However, a straightforward and less expensive technique is the use of air temperatures. The guidelines are based on the assumption that the critical period ends, and load restrictions may be removed, when the ground has thawed completely. The primary equation developed for determining when to remove load restrictions predicts when the pavement will have thawed completely. This straightforward equation predicts the thawing index and is a function of the previous winter's freezing index. The amount of thawing required to completely thaw the pavement is about 30% of the preceding winter's freezing index. In other words, the thawing index equals 0.3 times the freezing index. For example, if the preceding winter's freezing index is 1,000 degree Fahrenheit days, then the associated thawing index is about 300 degree Fahrenheit days. To use this number to calculate when to remove load restrictions, add each day's thawing index, one day to the next, beginning with the start of the thawing period. When the cumulative daily thawing index equals the predicted thawing index, you may consider removing the load restrictions. For our example, the day the cumulative thawing index reaches 300 would be the day you could remove the load restrictions. In general, if the preceding winter's freezing index is about 400 degree Fahrenheit days, you can expect to enforce load restrictions for about 2 to 3 weeks. For a much colder winter, say with a freezing index of 2,000 degree Fahrenheit days, you may need to enforce load restrictions for about 6 to 8 weeks. The Washington State Department of Transportation made an early attempt to see how well the criteria on when to apply load restrictions worked. To do this, maintenance personnel examined pavement sections in Washington during February of 1986. This state route in central Washington had experienced a winter with a freezing index of about 1,000 degree Fahrenheit days and is classified as a thin pavement. This was the pavement surface on February 6. Note the water draining from a transverse crack. Heavily loaded wheat trucks were using the road. The thin pavement surfacing near the edge was breaking up due to the weight of these trucks and the saturated condition of the base course. Removal of a few pieces of broken pavement surfacing reveal the top of the granular base course. Note the free water. Excavation of the base reveals that it is completely thawed to the top of the subgrade. Clearly, the base has little strength in this condition. The calculated thawing index as of February 6 was 26 degree Fahrenheit days, thus falling between the should and must recommended levels for a thin pavement. In summary, the problem is essentially one of water in the pavement structure during thawing periods. For most agencies, the most viable solution to preventing pavement damage is to restrict loads during thawing periods. In general, maintenance personnel ask where to apply restrictions, how much to restrict loads, and when to apply and remove restrictions. The criteria that you should consider when selecting where to use load restrictions include the depth of freeze, which can be determined by the freezing index, the surface and base thickness, whether the pavements are on fine-grained subgrades such as silts and clays, and local experience relating to observed moisture and pavement distress and deflection measurements. When considering how much load to restrict, remember that North American practice and our studies analysis confirmed that if you need load restrictions, you should reduce the load on individual axles by about 40 to 50%. Again, if load restrictions are needed, a minimum of 20% is necessary, and load reductions greater than 60% are excessive. You should restrict loads after thin pavements accumulate a thawing index of 10 degree Fahrenheit days and thick pavements accumulate a thawing index of 25 degree Fahrenheit days following the start of the thawing period. You must restrict loads after thin pavements accumulate a thawing index of 40 degree Fahrenheit days and thick pavements accumulate a thawing index of 50 degree Fahrenheit days following the start of the thawing period. Thawing index is the addition of the difference between the average daily temperature and a reference temperature of 29 degrees Fahrenheit for each day of the thawing period. Load restrictions should be removed when the pavement has thawed completely. Our equation for predicting when the ground will have thawed is 0.3 times the freezing index. Remember that freezing index is the addition of the difference between 32 degrees Fahrenheit and the average daily temperature for every day of the entire winter. When your cumulative daily thawing index equals the predicted thawing index, you can remove the load restrictions. Please keep in mind that these guidelines are indeed just guidelines and are no substitute for the judgment of experienced maintenance personnel. However, we believe that these guidelines are a good starting point and that they will be valuable in helping you prevent pavement damage during seasonal thaws. For further information, you can obtain a summary of this videotape by writing the Federal Highway Administration, RD&T Report Center, HRD 11, 6300 Georgetown Pike, McLean, Virginia, 22101.